Alright, back to vids. So for this one, we will talk about a Venturi meter with head loss. Essentially, you're given manometers with taps before and after the choke. And then we're trying to figure out the flow rate through the manometer based on these values. So you guys might have related this to Lab 3 for those that somehow forgot or don't know. Lab 3 is essentially using the Bernoulli equation through a Venturi meter, and you find out that, hey, we have unaccounted for frictional losses that show up in the static pressure or the static head that you can directly measure. So, apologize for the graininess and lack of color. I was not given the high-res version with color, so here we go. But in essence, you are given this cross-section of a Venturi meter, right? So you have before is 0.1 meters, after is D. So we want to figure out the flow rate through this Venturi meter as a function of the small diameter. We are also given the head difference between these two manometers of 0.2 meters, and we are told that water flows through the pipe. Okay? So let's do it. Real quick, I have always hated the way that manometers are presented in class. So what I did was made a sketch in SolidWorks, and basically one way to think about these manometers and taps, think about it as they are tapped from the side, right? So again, flow is brought to zero right at the mouth of the manometer. So all you have to worry about is static pressures and pressure gain through hydrostatics through the manometers, right? So just note, at this point, right at the Venturi meter's tap, that will be the same static pressure on a collinear line right in the main of the flow, right? Pressure is isotropic, blah, blah, blah. Trust me on this one, we won't go through the exact theory as to why that is. But this is how I like to look at the manometers, okay? So you can see here that they are collinear. They have the same delta, or same Z naught, right? So that's the way I look at it. So let's see some key assumptions. For one thing, we have the continuity equation of incompressible flow. So the Q at 0.1 is the same as the Q at 0.2. Once again, velocity is brought to a zero at the taps of the manometers. Basically, it's just saying, hey, use hydrostatics. The ends of the manometers are exposed to air pressure. So you could say the end point when we do the hydrostatics, those will be the same pressure. Energy must be conserved. That's just like the law of the universe. So for fluid dynamics, we like to use the Bernoulli equation. And points 1 and 2 are collinear. Okay? So let's turn these assumptions into equations. Here's the flow rate. A1V1 is equal to A2V2, where the areas of these are given. For now, just to make the math tidier, don't do the math of 0.1 squared. Just leave it like this. Trust me on this one. You can if you really wanted to, but you'll see that there's just a lot of canceling that happens. Velocities are brought to the zero of tap entrances. So once again, we're going to use hydrostatics. And the manometer ends are exposed to air pressure. So here's the hydrostatics. We start at 0.1, we work our way over, and then we go up to Z naught, so we lose pressure. And then once again, we go up even more, so that's Z naught plus 0.2 minus Z naught. We end at that point, and we're exposed to air pressure, our final pressure, okay? So if you don't know how I did the hydrostatics, see the video that I just made on hydrostatics. So we have these two equations. Energy must be conserved, so this is just our Bernoulli equation. Now, some of you may be wondering, hey, wait, I've seen in later classes or later labs that we can modify the Bernoulli equation by adding to this end our head losses due to friction and stuff like that. Why aren't you doing that here? Well, I kinda am. See, these P1 and P2 terms, they're very loaded. So you can see here in the P1, we actually are going to have an extra term. So if I really wanted to, after I threw everything together, you would actually have like a ghost term right here, and that would be your head loss after you go through the choke of the manometer, right? Anyways, so points 1 and 2 are collinear, so these effectively cancel out. We have 4 unknowns, 4 equations, so let's get into it. The unknowns being A1, V2, or I'm sorry, V1, V2. D is kind of given, it's just a variable that we're using. And then P1, P2, we do not know. So 4 unknowns, 4 equations. Same thing with Z1 and Z2. We didn't know them either, but you can see that they canceled out. So we are all good to go. So let's put it all together. Ignore that arrow, it shows up later. So doing some math, right? We can relate V1 to V2. And then we can rearrange P1 as this. You'll see why this shows up later. P2. And then we can throw 1 through 3 into into the 4th equation, right? So you'll actually see that the P atmospheres, they will cancel out. The rho H2G Z naught and rho H2O G Z naught, they also cancel out. So what we are left with is just this equation, right? So I did some extra math here. I just multiplied through by 2, and you can see that I've substituted V1, the equation for V1 here, and we are left with this equation. You can rearrange this and get the following. So I'm just going to divide 0.4g divided by this value, take the square root of that, and we are left with V2. So you can see here that we are very close to being done. All I need for the flow rate is to multiply V2 by A2, and we get our flow rate, right? So me personally, if I was your professor, I would say this is adequate enough. You don't have to do any extra math that might get the wrong answer. Something important to note is that you're actually limited in your choices of what the diameter can be, because you can't have a negative value under the square root, and nor can you have a 0 under in the denominator. So that's kind of cool. And if you want to rearrange this, you most definitely can. This is your most exact value. I would happily accept this. You can also just quickly take out your calculator and turn the crank on this. But so that is a problem we worked out in class. Let me know if you have any questions, comments, or concerns. Good luck with finals.